Hello. Today we'll be talking about all about expected value. And so we'll start off with just some defining what expected value is, kind of giving some intuition with an example. And then we'll talk about different cases of expected value. We use it with linearity expectations, including with indicator random variables. And we also will do kind of a more advanced example with the law of total expectation from Groupwork 8. So without further ado, we'll go ahead and get started. So what does expected value mean? So kind of definitionally, we can see, okay, the expected value of some random variable x. Well, we'll get that by, we'll take each event in our sample space and we'll say, okay, what's the probability of this event that's occurring? And then we'll multiply that by, well, what is the value that this expected value takes on when we have the sample space S. So remember this event S. So remember that a random variable maps from something in the sample space to something in like the real numbers. So we often like write this kind of to think about, okay, we'll take out all of like the actual outputs of a random variable. We'll call this little x, and we say, okay, the probability that our like random variable has this output x, and then times the what is the actual value of this x is another way to write it. And so kind of thinking about an example, what if we say we're going to play a game? And in the game, we'll say if you win, you earn $1. And if you lose, you lose $1,000. But the probability that you win is quite high. The probability you win, we'll say, is 1999 out of 2,000. And the probability you lose, that's just only 1 out of 2,000 times. So the expected value, kind of like the idea is, what do we get on average? And so to kind of compute this, we can say, okay, expected value of, we'll say maybe y is like the winnings. Maybe I'll call it w actually for like the expected, like the winnings. So expected value of my winnings. Well, that's the probability, or we'll sum over each events in my random variable, and so I get the probability that w equals w times the value of w itself. And so okay, this first event is, okay, we earn $1, and so this probability was 1999 over 2,000, and then the value here was just $1 is what we won. And then we also could lose, and so that's 1 over 2,000 is the probability we lose, and the value in this case is 1,000. And so we just sum these things together, and we end up getting and this should be negative 1,000 because we're losing the money, right? And so we get 1999 minus 1,000 over 2,000, and so we get 999 over 2,000. And so what we get is kind of our result is we expect when we play this game, we'll win on average a little slightly less than $0.50. But this actually is like not really a monetary amount you can earn here, and you never actually win this, right? You always either earn $1 or you lose $1,000. But you can think about it kind of as if you were to play this game infinitely many times or some really large number of times, like billions of times, and then you say, okay, what's the average amount that I earned? You say, okay, the average amount I earned per game was this like little less than $0.50 here. It's $9.99 over 2,000. And so kind of can help you develop some intuition about what is expected value actually measuring, and then like how do I compute it. So I think if you understand that example, kind of well on track to work through the next one. And so yeah, so we've gone through some definition and some intuition and an example, and now we're going to talk about linearity of expectations. And so this saying we have two expected values, and so we think about, okay, I have some two random variables here. So I have x1 is a random variable and x2 is also a random variable. And so these, I'll say these can be independent or dependent. And so this holds in either case. And so if we're saying, okay, what's the expected value if I took this event and I added the second event here, and we say, well, that's just the expected value of this sum here. So I take the expected value of x1 and then I add it to the expected value of x2. And this is maybe a little bit like unintuitive, so let's kind of visualize it here. So what if we had a second game? I'll say game 2, and game 2 is we flip a coin, and we'll say this coin is somewhat biased, so the probability of heads is 2/3, the probability of tails is 1/3, and we'll say if we get a heads, then we'll win we'll win $3, and maybe we'll lose $3 if we get tails. And so, okay, I can find the expected value of this game, and maybe I'll call this expected value of my game here is so I can think about, okay, each event. So the first event is I win $3, so the probability of this happening is 2/3, and the actual event itself is $3. And then I also could have 1/3 chance of I get negative $3 or lose $3, and so I get 2 minus 1 is 1. So on average, I'll win $1 from this game. And so I actually thought, what if I played both games? I can think about, okay, what's my expected value of my winnings from the first game plus like whatever I got from the second game? And I could say, using linearity of expectations, I can say, well, that's the expected value of the winnings I received from the first game plus the expected value of my game. And so then this ends up being, I think we said $9.99 over 2/1000 of $1 plus $1 here. So I could say, okay, that's, yeah, I don't really simplify this very nicely. I guess I could say 2,999 over 2,000 if I'm read it as an improper fraction, but yeah. But basically, like here, in this case, these things are independent, right? So like the outcome of my first game doesn't really affect the outcome of my second game here, but we can actually make a claim that's even stronger. We can say that even if these things are dependent, we can make this claim that if I add two events, and I can explain this to more things, then I can just take the sum of the expected values to get an expected value of a sum. So let's kind of work through this more powerful example here, and we'll do that with something with indicator random variables. So this will look very, very similar to a problem on homework 8. You can just kind of modify it very slightly. And so the idea here is we'll take our same like coin here, where again the probability of heads is 2/3, and the probability of tails is 1/3. And we're saying we want to, so we're tossed it 10 times, as in the homework problem. And so we get some like sequence of like heads and tails. So maybe I get like, I don't know, something that has some heads and tails or whatever. And so we're wanting to say, we'll define x is a random variable that will say, okay, the number of times that we get like HH. And so, for example, here I have like a heads. Here I have a heads. I have a second heads here, third heads here. So I'd say, okay, here I have like this appears 4 times. And so we're wanting to find the expected value of the number of times this like this double H sequence appears. And so to do this, it's not initially clear how do I do this for like the entire like 10 coin toss. I can't really easily like say, okay, like what is an event here. And so it's kind of to help us along, we'll define indicator random variables. And so I'll say, yeah, we can talk about xi is saying, so an indicator random variable we know basically it will measure like the ith thing, and then we'll say, okay, it's 1 if my condition holds, and it's 0 otherwise. And so, yeah, I guess kind of intuitively, if we can define indicator random variables that somehow map to like each of these things in this sequence, then I can instead, let's say, okay, the expected value of my x is equal to the expected value of some number of indicator random variables. May have like n indicator random variables, and then, well, I can use linearity of expectations here and write the expected value in terms of the sum of these indicator random variables, their expected values. So here's where linearity of expectations comes in. And so I can write this in terms of the sum, and then I'll be able to find the overall expected value. So what actually should I define my variable as? And so here we define it as, well, we'll say, okay, this is 1 if we get like a double H. And so we have like, okay, the ith thing. So maybe I'll say this is the first one, second, and so forth. And so we'll want to have if we have like the ith and like the I plus 1 term are heads, right? And so we could, in this case, maybe, okay, the first and second are heads, or here like the, I don't know, fifth and sixth are heads, sixth and seventh, and so forth. And so will be 1 in that case, and will be 0 otherwise. And so if I actually, okay, find what's the expected value of some xi. Maybe it's a little hard to visualize, but maybe I can actually, what's the expected value of x1? And well, okay, x1 means I have to get a head in the first place, head in the second place. And so that'd just be, I have 2 heads basically. And so I would say, okay, that's probability of heads was 2/3. So I would say, okay, we have 2/3 times 2/3. So we get 4/9. And then actually the expected value of x2 was the same thing, right? Because I'm asking for a head here and a head there. Both have probability of 2/3 of happening. And so yeah, so here then I can actually say, okay, each of these is 4/9, and I have yeah, so I get 4/9 plus 4/9 plus 4/9 each time. And how many of these do I have? Well, I actually only have 9 of these, but because kind of the last one here, like in position 9 is like 9 and 10 together. And so I have the, if I do 10, I have an off by 1 error, which is common to computer science. But yeah, so I do this 9 times, then I get 9 times 4/9, and I get, okay, I overall expect to have 4 sequences of HH with my like bias coin with heads probability of 2/3. And so how do we do this again? Well, we said I can kind of break up my sample space into this like different events that like these x's or like x1, x2, x3, x4, x5, and so forth. And then I can ask, I want to find the expected value of these events. And these events are using the indicator random variables. And then I can use linearity of expectations and say, okay, even though these events are dependent, I can rewrite this in terms of e of x1 plus e of x2 and so forth. And then each of those had the value of 4/9. And then I multiply that, and there were 9 of them. So then I get 4 as my overall expected value. And so I will say, yeah, again, these are dependent. So if I had a yeah, like a an H, like if I had some H tails or whatever, like if I couldn't have like a HH here, maybe I can't have an HH like here as well, possibly. And so we could have some dependence here, but we still can use linearity of expectations. All right. So that was the linearity of expectations. Fun. All right. Now we'll talk about the law of total expectation, and this appears in Groupwork 8. And so yeah, so what was this problem again? So we're saying we're wanting to solve this coding challenge. So again, this is group work 8, problem 3. So we have a coding challenge. and we say we have so the probability we're saying we have less than, or we have exactly x 30 minutes to solve is 1/4, and I'll also write that as 0.25, and the probability that we have 15 minutes and fail is 0.5, and then we have a 0.25 chance of you take 90 minutes and fail, and so yeah, here we succeed. And so the idea is like, when will we succeed, or what's the expected value of if we say we'll have t be like the number of minutes until we succeed, and then we'll ask, okay, what's the expected value of this t? And so initially it's kind of like difficult, right? Because here I actually don't like so here's the only case where I actually like can say, okay, I succeed, and this probability is like 0.25, and so I can write that, okay, that's this probability is 0.25, and then the time is like 30 minutes, so I could say, okay, I have 0.25 times 30, but then here I have a 0.5 probability, but I actually don't like, I don't end here. Instead, I've failed. I have to kind of try again, and so I actually kind of reset here, and I have to kind of think about it from the get-go. And so then we can kind of use this idea of this law of total expectation. So law of total expectation is saying, okay, we have some events that partition a problem, and so this is kind of similar to the idea of we have like the equivalence classes. If you recall, yeah, equivalence classes like partition an equivalence relation, and so it's kind of like we'll cover all of like the equivalence relation. We have a similar idea of like we can partition this this like sample space, like all the possible results here with we'll say we have maybe like we have M1, M2, and M3, or we could have some number of M1 to Mn that do this, and we say, okay, well, if this value of this of t is the same as the value of t given M1 times the probability of M1 plus the expected value of t given M2 has occurred times the probability of M2 occurring plus the expected value of t given M3 occurred times the probability that M3 has occurred. And so it's kind of very similar to the idea of conditional probability. So I think about a conditional probability here is like it's like similar to this. And so that can help you build some intuition for that. And so then, yeah, so then we can kind of plug in things here. So expected value of, so if we know that Ishan has succeeded, like so the expected value that given that we know, okay, we have like this, we'll say M1 is he succeeds in 30 minutes, M2 is that he fails in 15 minutes, M3 is that he fails after 90 minutes. And so if we know that he succeeds, like he'll succeed in 30 minutes, like we know that event's happening, then okay, the expected value of this would be 30, right? Because it just took him 30 minutes to solve it. And so we start off with like getting E of t be equal to 30, and then the probability of this happening is 0.25. And then I'm gonna also write this as 1/4. Okay, and then we ask, okay, well, the probability, I know the probability of this like second event happening that he takes 15 minutes and fails is 1/2. But what is the expected value? So this is saying I know that we like fail after 15 minutes. So basically this means that we spend 15 minutes, we fail, then we have to start over. And so you actually rewrite this as saying, well, it took me 15 minutes plus like my expected value of however long it would take me like normally. And so I can kind of, this appears on both sides of the equation. And so I can kind of work with that. And it's a similar story for my last event where I say, okay, I take 90 minutes and then I kind of reset. And so I have 90 plus the my like other like excess value. Here, like if I hadn't considered like resetting, and so then I can then solve this via some algebra here. And so yeah, I could work out what those would be. And I eventually would find that okay, I have the expected value of um, this time is it will take me 150 minutes overall. And so I would, yeah, just be doing some algebra there to get that. Which I won't do that just for time's sake. But yeah, so this is a kind of yeah, gone through a lot of things, all about excessive value. So everything from basic attention to like the law of total expectation. And so yeah, that was yeah. Enjoy working with excessive value and take care.